Swayam Prabha. Digital India. Educated India.
Okay. So, before we take up this today's topic, that is oxidation in heterocyclic chemistry, we will go back a little bit and try to solve the problem we gave you last time. I do not know how many of you have worked out. How many? There are two kinds of problems. One is to unite two aromatic unit, I guess, two aromatic units or one aromatic unit or one aromatic units. Anybody of you have done it? It is just a sort of a somewhat equivalent to a vicarious substitution reaction. That was a reaction between a molecule of this kind. When I say a molecule of this kind, we should not talk about this kind, we have to tell the specific name. By now, all of us know what is the name of this nucleus. What is the name of the nucleus? Quickly. Good, acridine. And so, if you have these, and then I think we are to make a compound where you will have this acridine nucleus, and then you have to substitute, I guess, sorry, ester unit with a, let us say, an aromatic unit. So, quite obviously, and the reaction mechanism demands that in addition elimination is a process. Addition elimination is a process for a pyridine nucleus with an electron withdrawing groups at the 2 position or 4 position. In this case, that means what you have to do, you have to take the corresponding ester, that is it, corresponding ester and a base. Occasionally the sodium hydride works, and all of us know that these two together would give you corresponding anion here, and then anion goes to the carbon having the chlorine. So, then addition takes place. So, eventually what you will get? You will get sort of a reaction which is reminiscent of a Schiff's base. So, negative charge is produced, and what you will have now? You will have an addition product. So, Cl, CH, and then phenyl and CH, the methyl ester, right? And what next? I think again a vicarious substitution reaction, and but in this case you do not have to do that. You can straight away eliminate this. This is a typical like Sanger reactions. Okay. So, this is one of these ways, and how to get to this acridine nucleus is not that easy though, but in this case it is pretty easy. How to get this acridine nucleus? And okay, I will tell you something else, maybe it is pretty similar to that. For example, I give you also this problem that if you have an ester of this kind, and then what are the next reactant? Aniline. So, what do you expect? What do you expect out of this? The reaction condition is, let us say, toluene. Reaction condition is toluene, and normally for any sort of condensation reactions with amine, acid is required, not a base. So, paratoluene sulfonic acid. So, what do you expect quickly? Not really. Immediately what you would expect, enamine, right. So, what you get is an enamine and an ester here. What next? This is a typical reactions in heterocyclic chemistry, ring closure. So, enamine also under strongly heating condition undergoes cyclizations, just like amide formations. If an ester and amine in seal tube heated together at high temperature gives corresponding amide. So, similarly, it is an internal amide, and in this case a special kind of solvent is used called ditharm. I do not know how many of you know. It is a chemical that is devised or that is sold by Dow Chemicals of USA. Dow Chemicals is a high boiling liquid, and this liquid can be boiled to around 400 degree centigrade. That is the highest temperature. That means at 400 degree centigrade it is a liquid. Okay, there are very few, and it is a mixture of biphenyl. So, basically a solvent plus the corresponding diphenyl ether. So, it is a mixture of two chemicals, is a high boiling solvent. So, once you have these, then internal amide or vinylogous amide is formed, and what you get is this corresponding ketone, and this is NH. This is not this. What next? I mean, very similar, only one of the ring is not aromatic. So, if you treat this with a standard, again a POCl3 is a very standard chemical in heterocyclic chemistry. What do you expect? Quick. What do you expect? You expect this aromatized compound is sort of like acid chloride. It is a standard protocol, and this protocol also used for making the analogues from quinine analogues, means these antimalarials, primaquine, pramaquine, all these. Okay. And if you want to, let us say, go to the acridine nucleus from here. So, what you have to do? No, that is the trouble. Yes. If I did not know, I would have also answered this question, these questions by saying DDQ, but that is the reason the next topic is about. So, I mean, why suddenly we identified oxidation in heterocyclic is a separate topic, because whatever we learnt about the oxidation in standard organic chemistry cannot be extrapolated to heterocyclic chemistry. Likewise, heteroatoms exert all kinds of special reactions. We have listed 12 different kinds of reactions. Also, those heteroatoms all create problems. Okay. It is not the standard protocol that whatever you have learned in organic chemistry should be extrapolated and should be applicable to all the heterocyclic chemistry. The presence of lone pair itself can complicate the situation. So, for example, the case like if you want to try to give DDQ oxidation, there could be a complication, number one. Number two, since you are young, so you should have a knowledge about the problem that DDQ is very expensive and very expensive. So, you should find a substitute for DDQ if you can find out. Okay. There are quite a few, for example, palladium carbon, selenium, those are all old, but you have to have a new reagent that can cause dehydrogenations or aromatizations, all these things. Okay. But there are not many though, there are not many. That's a part of the topic, today's topic. So, we will talk about it, and so that means oxidation. So, oxidation is a problem in heterocyclic chemistry, primarily because of the presence of the lone pair, okay, and the presence of the heteroatom. So, whenever you think of oxidation, actually we think of oxidation of the alcohol to the ketone, alcohol to the carboxylic acid, and those things, all these things. But when it comes to heterocyclic chemistry, you have to be little cautious, because the oxidation can take place at the nitrogen center, heteroatom center, in the neighboring center, onto the nucleus, and in addition to the existing functional groups, etc. So, you have actually many more options, many more things to be considered before you choose a right oxidant. Okay. And so, before we come to these other details problems, let me just very quickly, many of you have attended my 4th year class. So, we will again talk about a little bit for those who do not know defining oxidation. Normally in high school we say oxidation means addition of oxygen, removal of hydrogen, or else one more definition, the loss of electron. But when it comes to organic chemistry, we have a quick formula how to find out this oxidation number, right. And if you recall, let us say, right, suppose you want to let us say you want to put okay, this is a very simple one. This is a simple one though. In this case, what you see, just if you formulate the, if you just calculate the molecular formula and you see this, there is a difference in oxygen. So, addition of oxygen, that is very quick, but most often the problems are not that simple, that we have all different kinds of problems, right, all kinds of different problems. Let us say I will to make this problem little tougher, whether it is an oxidation or reduction. Okay. Let us say we are talking about this one, and you recall that oxidation number given to a compound is determined by this number of oxidation number, number of cycle, number of multiple bond, multiple bond, and number of heteroatom, and then minus 1. So, similarly, in this case you have to oxidation number of this product could be same formula. So, if this is the master formula and master formula, then for the left hand starting material, number of cycle is 1, number of multiple bond is 1, number of heteroatom is 0 and minus 1. So, oxidation number of the starting material is 1. Okay. Now, if you go to the right one, so number of cycle is 1 and then heteroatom is 1, no double bond, right, minus 1 and equal to 1. So, delta oxidation number 1 minus 1 is 0. That means, there is no change in the oxidation number, that means, this particular transformation does not require any oxidizing agent. So, that means, no net oxidation is taking place. This is one of the very simplest way of looking at it. Okay. But when it comes to heterocyclic chemistry, you have to add one more parameter. What is that? No, lone pair of electron. This is the modification. Actually, this formula was given by somebody else from US. Then I have modified that for the heterocyclic compounds. So, you have to add one, and I have published a paper in Journal of Teaching Organic Chemistry long back in 1997. If you are interested, you can go to my page and you will find the article there. And so, what you do, you have to basically take care of the lone pairs. Okay. So, then that means, whatever these items are added plus number of heteroatom. This is not only a good formula for finding out whether the reaction is oxidation or reduction, it also tells you how many equivalents of oxidizing and reducing agent would be required. For example, if you take, let us say if you have this cyclohexene and let us say you want to do the from cyclohexene to cyclohexenone. So, what is the level of oxidation? How many electron oxidations are required? So, for the cyclohexene oxidation number is 1, and the cyclohexenone, what is this oxidation number? 1 cycle, 1 double bond, no, 2 double bonds plus 1 heteroatom minus 1. So, 3. So, delta oxidation number is 2. That means, you need actually 4 electron oxidation. You need 4 electron oxidation. Okay. So, this is actually a very good guideline actually. I mean, so far I have not seen any exception to this rule. If you have come across, in fact, this could be, I mean, applicable to almost any kind of organic reaction. If you come up with any exceptions, please let me know. Okay. And now, in the case of nitrogen, the problems are serious in organic heterocyclic chemistry. Just to give a background why it is so serious. For example, if you have a primary amine. So, what is the next phase of oxidation? Primary amine, one can quickly say it can go to hydroxylamine, this is a standard one. If you want to further oxidize this, then further oxidize NO2, right, NO2. So, this is a typical one. Now, let us say if you have a secondary amine, what do you expect? Secondary amines, okay, fine. Why NO? I can simply write this, right, okay. What next? What next? You have seen it, oxyl, right, nitroxyl, like in tempo, maybe we will talk about today. And so, this is known as nitroxyl radical, So, like this, I mean you have all kinds of them actually. Then what else? If in fact, from this also you can have an oxidation. If you have a carbon here, I think this carbon here, let us say carbon here. So, you can go to this, right, let us say R prime. Now, this is carbon, what is it? You can from secondary amine straight away go to the, you should know by now, what is this, right, nitrone. So, that means you have so many varieties of these functional groups arising out of nitrogen. Okay. Like then also let us say if you have a tertiary amine, if you do an oxidation, what do you expect? N oxide. So, N oxide, that means you have this multitude of the functional groups which can be derived from these amines. This is only for nitrogen. Now, similarly, when you have a sulfur compound, I think many of you know now, the next step is the disulfide, then you have sulfoxide, right, these are all things. Then what next? Sulfone. Similarly, if when you have let us say SH, it go to SOH, sulfenic acid, then 2 oxygen sulfenic acid, 3 oxygen sulfonic acid. So, like this you have all kinds of probability, So, you have to be little careful, but what we can say that it is very difficult to predict a right oxidation or predict and right oxidizing agent for heterocyclic chemistry. Okay. So, it comes with little experience, it comes with little culture of chemistry. So, we will have more and more examples just to justify that under varieties of situation, varieties of oxidizing agent could be most appropriate. Okay. Let us take up a simple example, for example, which is really unpredictable. It is a primary amine, right? Primary amine. How to convert this into this?
Titanium trichloride.
Titanium.
Trichloride.
That's the first oxidation.
Okay. So, let us see first whether it is an oxidizing agent, whether it is an oxidation reaction or not. I think little obvious, right, somewhat obvious. Somewhat obvious because you have put nitrogen takes up the place of oxygen. So, oxidation number remains same, you have a double bond, etc. So, oxidation reaction, that is perfectly all right. If you are very strong in bioorganic chemistry, you can quickly say how to oxidize this. Who knows? In bioorganic chemistry, there is a very famous reaction, starts with the name oxidative.
Okay. That transfer between amine.
Right, oxidative deamination.
That PLD mediated.
Oxidative deaminations. So, that is perfectly all right. So, you form a Schiff's base, isomerize, hydrolyze. So, then that is just oxygen gets transferred to this, that thing. Okay, but in this case, if you do want to do chemically, and as I said before, that is somewhat unpredictable, but like say the silver nitrate and sodium perdisulfate and alkaline medium. How do you come up with this? Absolutely no idea. It comes from the experience, it comes from these findings from the literature. There is no way directly one can do it. So, what you eventually get basically a dehydrogenation takes place. If you recall, in the last class I talked about that alpha radicals, alpha to the nitrogen, alpha carbonium ion, and then this carbines, they are all stabilized by nitrogen. So, that is the driving force why this hydrogen is transferred to the oxidizing agent and forms the Schiff's base. Once the Schiff's base is formed, there is a likelihood that this would undergo under the water or alkaline medium. Alkaline medium, it goes to the corresponding ketone, but these are not a very simple reactions, and in certain cases which are permissible. Now, I take up a very similar molecule, just consider a similar molecule, let us say this one. So, this basically gives you an idea that silver nitrate, potassium, sodium pardisulfate could be an oxidizing agent compatible with heterocyclic compounds. Likewise, there is another oxidizing agent many of you probably are not familiar with, but very famous oxidizing agent, which comes from acetone and oxone. Anybody knows? Again, I think in fourth year I talked about a little bit of this. Oxone is a famous. In my lab we have potassium monopersulfate, potassium hydrogen sulfate, and potassium sulfate. It is a tri-salt mixture, but the active component is potassium monopersulfate, KHSO5, carriage acid, corresponding salt of the carriage acid. So, if you mix with acetone, it gives you a nice product which could be distillable, but only but it is not commercially available. If you whenever it is required, you can make it in the lab and then convert this, and this is nothing but again it is a heterocycle. What is it? This is nickname is this oxygen, I think the nickname is this dimethyl dioxyren. Okay. Very clean oxidizing agent, and many times it gives nice clean products. Okay. So, if you let us say in this particular example, what do you expect then? I mean, all these possibilities are there, right? All these possibilities, it can form the imine, it can form the N oxide, it can form this hydroxylamine, it can form the nitro, all these things, but it is such a powerful oxidizing agent, it straight away. So, that means this will give you just some idea that it is a very powerful oxidizing agent. It gives the corresponding nitro compound. Okay. Likewise, many of you have studied this before. Let us say anthranilic acid and same product, and if you are given to convert this into the corresponding NO2 and the carboxylic acid, often what you do, you do metachloroparbenic acid, something like that, right. But in this case this is perfectly all right. One can also suggest, let us say potassium permanganate, but potassium permanganate will give all kinds of things. What are the things? If you have an aromatic amine, potassium permanganate will give the corresponding nitro, nitroso, and then azo compound means dimerized, azoxy compounds, all kinds of things. So, that means nitrogen actually makes the situation very complicated, unless and until you know of this oxidation rightly. Like say let us say now this is again something quite unlikely. So, again this is an aliphatic amine, right. This is next very similar to this. If you try to do oxidize in analogy with the previous one, one would expect that the reaction would give you corresponding NO2, but actually the reactions can be interrupted at this stage, NHOOH, hydroxylamine. Okay. Often if you are asked how to make hydroxylamine, normally people start with nitro compound and moderate reducing agent gives you the right, very similar, but mind it, molecular merger cannot take place in acidic medium, it will straight away go to the corresponding NH2. So, then all these problems are there, and like say this is a very important topic. This is important oxidizing agent. Let us say instead of manganese, potassium permanganate, if you begin with MnO2, let us say you have heard this, you have read this in BSc. No, BSc you have read. I can still vividly remember Finner's book on the left hand side, that I remember, benzoquinone, right. You see, but also you can same reagent can give, what is this? What is the name of the molecule? Azobenzene. It is not diazobenzene. 2 nitrogen with this azobenzene. Okay. Let us look at the contrasting behavior of potassium permanganate. Let us say you have 3 methyl pyridine. Now you want to oxidize this to corresponding carboxylic acid. I think all of us would be able to, right, give the right answer. What is the reagent? Very good, potassium permanganate. This is a very safe reaction in the sense that you do not the nucleus, pyridine nucleus is deactivated, it is not subject to oxidation with a very strong reaction. So, side chain is oxidized in analogy with the benzene chemistry. Okay. Now, let us take up another molecule. I think it is very similar, again a 3 substituted molecule, but in this case the reagent is this one. Many of you know the nucleus is pyridine, sorry, nicotine nucleus. Now, I do not give you the product, you tell me the product. If I let us say treat this with HNO3, what do you expect? Now, things are a little more complicated, you have to think about it. It has an aromatic nucleus, it has an aliphatic nucleus, it has an aromatic nitrogen, you have a non-aromatic nitrogen and this thing. Okay. But the reagent is nitric acid. So, the first thing that to take place is the protonation of both the nitrogens, that is perfectly all right. But also together we know that nitric acid is a very strong oxidizing agent. So, it will oxidized and it can chew up the whole molecule to burn it, or you can give it a nice clean product. Okay, to give you the answer, it gives a clean product. Okay, that could be the first, yes, that could be the first, what he said is perfectly all right. Actually, double bond O could be there. Let us say further oxidizes. So, powerful oxidizing agent, actually it goes to this one. So, that means the aromatic nucleus is so deactivated, this only this aliphatic portion is, so it is a side chain just like toluenic acid or benzoic acid. And okay, quite similar to that. This is not a okay. This is let us say somewhat, it is not a purely oxidizing agent. Let us say you have proline hydrochlorides. Now, I treat this with triethylamine and DCM, that is dichloromethane, and then whatever the residue is obtained, it is treated with NCS. NCS stands for N-chlorosuccinamide, right. So, what do you expect? See, N-chlorosuccinamide also is an equivalent to an oxidizing agent. It is a chloronium. So, chloronium ion, brominium, chlorine, bromine, all these things towards the right hand side of the right top corner of the periodic table, all these atoms and reagents are oxidizing agents. So, what do you expect? So, basically triethylamine abstract the HCl present in this. This is salt, hydrochloride salt. So, makes it free proline ester. Thereafter, you treat that with NCl. So, what is the first reaction you expect? NCl, very good, that is it. So, once you know that the product is NCS, that is it, and this is not a stable one, you can guess why. because you have a conjugation to be played. So, it gives you the corresponding Schiff's base, So, if you look at the starting material and the product, the difference is basically dehydrogenation. So, it is again that means this is just an example to show that in chlorosuccinamide could be an dehydrogenating agent or oxidizing agent. And you have all, I mean just these are all little bit of the recollections, some of them are recollection. For example, if you treat these molecules dihydroquinoline and you want to do the dehydrogenation. It is a serious problem though to corresponding quinoline, but you all know the answer though, like DDQ would not be a viable answer. Reason being quinoline is so cheap, quinoline is let us say 1 liter maybe 500 rupees, but DDQ is let us say required DDQ 10 grams or 100 gram DDQ could be costing you 10,000 rupees. So, DDQ is not a right answer for this sort of transformations. Any suggestion? There are many oxidizing agents which often we do not think about. Nitric acid is, you can understand, nitric acid is not a good one. See, these are the things you have to think about. Now, at this stage, making a good choice of oxidizing and reducing agent, whatever the reagent in organic synthesis is tough, especially when you have a heteroatom. See, nitric acid can, all of us know, nitric acid can cleave the carbon-carbon double bond, like cyclohexene converted to adipic acid. Have you seen the experiment done before anywhere in lab? Just boil nitric acid, put cyclohexene or cyclohexanol or cyclohexene, all of these chemicals will be converted into in no time, in 10-15 minutes to corresponding nice crystalline solid of adipic acid. So, such a strong acid actually, a strong oxidizing agent. So, you cannot think of not only that, many of us know aniline undergo very facile nitration. So, it is equivalent to an aniline actually, it can lead to nitrate product. Nitric acid would not be a good choice for this sort of oxidation. So, palladium carbon, that should be all right, palladium carbon should be all right, that should be all right. But I will give you an example where palladium also diverts the reaction in other directions. But the best thing would be if you recall a reaction you have studied in BSc, where you put nitrobenzene, no, right, not as a solvent, that is also a reagent, right. Krauss synthesis, Krauss quinoline synthesis. So, okay, and let us say this is something different. This is very useful these days. Let us say you have an amine, secondary amine, and basically by giving this example, I am trying to show you some of these usefulness as well as the limitations. For example, if you take hydrogen peroxide and secondary amine, what are the products? I have already told you. First, it goes to hydroxylamine, then next is nitrone. So, in this case, if you take sodium tungsten, it will nicely give the corresponding nitrone. Take this similarly, take isoquinoline. It goes to the corresponding nitrone. Okay. So, that means this is just hydrogen peroxide, mind it, hydrogen peroxide, secondary amine is a nice combination, and sodium tungstate is catalyst basically. Your stoichiometric oxidizing agent in hydrogen peroxide, it straight away give to the nitrone. It is a nice preparation of the nitrone. Okay. And occasionally the variations are there, but basic oxidizing agent is hydrogen peroxide, and occasionally sodium tungsten is replaced by hydrotalcite. It is basically a silicate kind of catalyst, silicate. Nitrobenzene after reduction it gets to nitrosobenzene. Okay. Now, again let us say probably we also ought to have in our mind a possible oxidizing agent. Often we do not deal with or we do not talk about it. Let us say add methanol, then it can be converted into corresponding this methoxy compound. This is very easy. That means, alpha position can be substituted by methoxy, again due to the lone pair effect. The lone pair of nitrogen can stabilize the corresponding carbocation, etc. So, and oxygen has a lone pair. So, what do you expect that there must be some sort of a carbocation here. That means, hydrogen should be removed from there, and how do you do? There are plenty, there are plenty of oxidizing agents. One of them many of you probably heard of, CAN. Anybody knows? Very good. Steric ammonium nitrate. It is a very famous reagent. Actually, famous reagent for oxidizing dimethoxy benzene to quinone, and also for oxidations of the alpha positions of nitrogen. Okay, that's it. But obviously, you have lot of wastage. But one of the most successful green chemistry oxidation is electrochemistry, electrooxidation, anodic oxidations. Okay, so electrooxidation is a very important step in organic chemistry. Often we do not deal with, but if the reaction takes place, the reactions are very clean, and it is often it is often rather used by Japanese chemists. They are very fond of the electrochemistry. Okay. So, many synthetic processes. In fact, I heard, I do not know, I have never gone to the there is a place called Kalyani in West Bengal. Okay. Not you. There used to be a factory, actually. They used to reduce nitrobenzene to corresponding aniline by electrochemically. That is what I heard. I never have been to the place. Okay. So, that means many simple reduction oxidations can be carried out electrochemically. If the reaction takes place, these processes are very simple. Many of you probably do not know the voltage requirement is very little, less than 10 volt is enough for all these organic transformations. Okay. And polymer industry also, electropolymerization is very useful. So, in this case, so what you get is just a nice functionalization at a particular position, and this material has been used for many synthesis. Okay. And then this is another example, maybe we can talk about. This is also a synthetic challenge, though. Synthetic challenge. Let us say, like say, if you take Rani nickel and you can simply heat it. What do you expect? Rani nickel should be an oxidizing agent, reducing agent. It should be no. Palladium alone is an oxidizing. Palladium is an oxidizing agent. Palladium in combination with hydrogen is a reducing agent. So, you have to be little careful. So, actually this is the way, and this can be dehydrogenated. That means 2,2 prime bipyridine, 2,2 bipyridine. This is how made, but the yield is very poor, less than 50% for sure. And then of course, the isomers, this 2,2 prime, 4 prime, 4,4 prime, all these things are there, but there is no simple solution. I just looked up this morning the Psi finder, and people have used it, but again then you do the cross coupling reactions. So, cross coupling reaction would require a pyridine, and then their bromo, particularly a 2 position bromine, again is tough. Let us say 2 bromopyridine. How do you make 2 bromopyridine? Typically you cannot go by the electrophilic substitution reaction or nucleophilic substitution reactions. 2 bromopyridine, how do you make? No, you do not. Okay, yes, idea is good, but when you form N oxide, then this most of the electrophilic substitution takes place at Good, 4 position. So, I do not have to teach much of this period in chemistry, 4 position, but again then the whole problem is that you have to remove oxygen.
No, sir. In this simultaneously prepared in
No. Mechanistically, oxygen is not removed during the bromination.
so PuCl2 is formed. PuCl2 is formed.
Okay, you consult the literature. Okay, basically when you form this N oxide, okay, let me just since we had been talking about this is again an oxidation kind of reaction, right. As if you use hydrogen peroxide, what happens? N oxide is formed, right. N oxide, normally acetic acid is given, it forms the paracetic acid and then is okay. And then if you try to the electrophilic substitution reactions, and often this electron philic substitution reaction takes place at 4 position. So, if you do a bromination, so it is likely the nothing happens to the oxygen, instead you get the 4 bromo N oxide. Then you use a low valent phosphorus oxychloride, then it comes out as an oxychloride or whatever. Okay. So, that means you have so many steps and then you do this cross coupling. So, this reagent is very expensive. Bipyridine is a nice complexation agent in metal chemistry, polymer chemistry. Okay. So, it is a tough problem. If you can come up with the right solution, and it should be publishable. You just produce biphenyl directly in a single step and more than 50%. This I am guarantee you this is a publishable result. Okay. So, I mean that means what I am trying to say, some of the problems in heterocyclic chemistry are existing today. I mean there are quite a few, and then let us say this is another quite often noted. Let us say you have an chloride, pyridinium chloride. How do you know you are dealing with a salt? Most of the heterocyclics are water soluble because of the nitrogen. Okay. Well, in this case, you just do a silver nitrate test. That's quite easy. But if you are handling with an unknown compound, whether methyl is there, too many like too many methyls here and there, this thing, that thing, it's tough. So, I mean, in the older literature, what people used to do is to reaction with potassium ferricyanide, and then a little bit of sodium hydroxide. So, what do you expect? What do you expect? You get it's a nice reaction though. That's how actually this nicotine compound was isolated. The structure of nicotine was established. So, you get a pyridone. So, that means potassium ferricyanide is a nice oxidizing agent. There are plenty of cases where you can do some. At the moment there are actually quite a few. Maybe one of you can take up this potassium ferricyanide, the use of potassium ferricyanide in organic synthesis. These days people are using potassium ferricyanide for the cyanogen reaction. If you have an halobenzene etc., you can substitute the halogen by cyanide using potassium ferricyanide, not at potassium cyanide. Okay. And there are other oxidative dimerations. For example, if I am almost sure, I may be little incorrect. Let us say this is, for example, this use paracresol and potassium ferricyanide. So, what do you expect? Let us say, just a guess, phenol, any guess? Okay. Now we know that potassium ferricyanide is an oxidizing agent. Potassium ferricyanide is where is it used? Largely used in a very popular reagent. Okay. Hints. Oxidation, alkene chemistry, surplus. What else? I have given you everything, all the details. Okay, read Caruthers. actually these hydroxylation processes, it is potassium osmate and the stoichiometric amount is potassium ferricyanide, co-oxidant. Okay. So, these are the things you have to remember. To be a good organic chemist, you have to remember all these things. In fact, we are getting older, we are getting forgetting all things. Okay. This is something different. This is as I said, I roughly remember this example. If you find any mistake, just let me know. Presumably, it gives, sometimes people say pumerar ketone, pumerar, not the pumerar rearrangement or Pamara rearrangement. Actually, it gives you something like this. Close. I am trying to get a thing. Something like this. Let's see. Some I think let me see. I am trying to something like this is formed. Maybe I have no little difficulty. One of the ring is aromatic, I know. Other is probably. Oh, okay, right. Now I got it. This. So this is called pumerar ketone. Okay, so it's an that means if you look at, you can just quickly find out whether it is oxidizing agent or reducing agent. Sorry, it is an oxidation or reduction. How do I know? It's a dimer. It's a dimer, right?
So, but quinone derivative.
That's okay, but you never know. Quinone means it cannot be oxidized, but the other side may be reduced. There is cyclization taking place. So, I mean cyclization is forming, means dehydrogenation taking place. Okay. So, again we just basically calculate that will be a nice way of looking at it. What is the oxidation number of this molecule? One cycle 1, 3 double bond and 1 heteroatom minus 1, so it is about 4, right. 1 cycle 3 double bond, 1 heteroatom 4. So, 2 of the molecules have been united from the atom balancing. So, that means total number of oxidation number is in this case is 8, right. 2 times 4 equal to 8. Now, look at this molecule. How many cycle? 1, 2, 3, and how many double bond? 4, 5, 6, 7, right. And sorry, 4, 5, 6, 7. This is 4, right. Oh, sorry, 3, right, 3. So, 3 and 3. So, 3 and 3, 6, 2 heteroatom 1 and 2, right. No, we have ignored role pair for both of them. Okay. So, minus 1, so it is now 10. So, 6, 7, something wrong.
So, dimer for
No. This is 4 and 5 cycle 6 minus 1. Sorry, aromatic ring means 4, 3 double bond, 1 ring, 4, 5 minus 1, 4, and there are 2 molecules. So, 8. In this case, how many? 1, 2, 3 cycle, and 3 double bond here, 4, 5, 6. Oh, so this is actually 6 actually. 6 double bonds, 2 heteroatom minus 1. So, it is 10. So, it is a clear case of 4 electron oxidation. Okay. Any case, this is just a nice example, and it is called oxidative dimerations, and so and let us give you one more example. That means, this is just is a secondary amine, and you can use oxone. Now, we know what is the oxone. Oxone is potassium potassium monopersulfate, right, and this is the active component, then others are potassium sulfate. So, again I mean it is quite difficult to predict, what is that, what is the final product. The final product it depends on the power of the oxidation. I mean we can go for the electrochemical series etc., all these things, but in organic chemistry those are of no importance, especially when you are a synthetic organic chemist. You just have a rough idea about which one is more powerful oxidation, which one is more specific towards nitrogen. So, had it been specific towards nitrogen, it will oxidize to the hydroxylamine. If it is a further oxidizing agent, then it goes to the nitrone. In this case, that is it. I mean just absolutely no idea. I mean it is a gives you the nitrone. So, previously nitrone was prepared by hydrogen peroxide and sodium tungsten. Here is an oxidation. There is another nice clean oxidizing agent is many, I do not know whether if you know or not, MTO. MTO MTO is methyl renate, just like osmium tetroxide. Also in this case there is this nice oxidizing agent. This is just to show that there is, in the case of heterocyclic chemistry, MTO also is useful. And then other thing, I think I guess we will ignore some of the things. Probably I will give you one more important thing here, that is an oxygen. Oxygen is a terminal oxidant. Suppose you have a heterocyclic of this kind, you treat this, okay, and you are likely to get this, and there are plenty of methods, you have seen it, but this also can be oxidized by oxygen, just oxygen, and in combination with I really do not know what is the use of this hydrazine. Hydrazine is added, and then what is this? Flavin. So, flavin of course is an oxidizing, flavin is an heterocyclic molecule. So, this is a bio-oxidation, you can say. It is Murahashi, a Japanese scientist Murahashi is quite famous for it, and by now probably you know the structure of flavins, right? What is the structure, Tanmoy?
So, paraquinone type, but nitrogen.
No, now we are in heterocyclic class. So, we will go by the heterocyclic nucleus. Okay. Okay. Flavin is something like, of course, it is a tricyclic first, you have to say. Then the two nitrogens are up here, and this thing is aromatic. What else we see? Then other two nitrogens are in 1,3 position. That is it. And then the rest is basically what you said is like a aromatic structure, a quinone kind of structure. Then the rest of the things, I mean I would not also know, but okay, just since I have a note here, so it's you can say this plus and this and perchlorate. So this is a nice actually oxidizing agent here. So what do you see? This simple oxygen can be used like the another example, probably you have to know. I think I will give you one more example, very similar, that oxygen is an oxidizing agent in heterocyclic chemistry, and let us say it's a pyrrole nucleus. How to oxidize, how to break this nucleus, and to do so, and one can quickly do this singlet oxygen. We have produced in our lab. I don't know, it's pretty easy to produce singlet oxygen. The regular oxygen is inert, all of us know, but how to make singlet oxygen? I think I told you before in 4th year again, recapitulate rose Bengal, right. So, rose Bengal also and similar molecule, there is one more dye commercially available oxygen plus rose Bengal. Rose Bengal, all of us know it, the name originates from Bengal, right, because Bengali women used to use vermilion, sindoor. Fourth year বলেছিলাম তো, okay. No, we should know, being Bengali we should know actually this originated actually, but the manufacturer is from Germany. German manufacturer made this, then to make it popular they gave the name rose Bengal. Okay. It is basically xanthine dye. Xanthine dye is also a heterocyclic molecule, right. What is xanthine? Quick. Xanthine again a tricyclic, just like palmarar ketone or fumarar ketone is this. So, you have then the other thing. So, right, you have a phenyl ring here, then halogen, in this case bromine, etc., etc. So, or else you can use I think we used eosine, it is a very similar drug, a similar dye, and then these singlet oxygen has a typical pattern of reaction. Normally it can undergo two different kinds of reaction in organic chemistry. One is yin reaction, other is the Diels-Alder reaction. In this case, because of the presence of the carboxylic ester, it would undergo Diels-Alder reaction, and the molecule that you get is this. So, molecule and this nitrogen will having the ester group E and the double bond, or else one can just quickly write this way. And this. So, now this is a process of oxidative dearomatizations. Your molecule was dearomatic, now it has been dearomatized. At the same time you have introduced oxygen. So, the oxidation has taken place. Exactly same, I mean we will continue a little bit with more of these oxidations of the compounds, aromatic compounds, heterocyclic compounds. Maybe we will also talk about little bit of these. We have quite a few more examples. I think probably we will take it up in next class, because it is a very useful process, the oxidation, and some of these selective oxidations also will be taken up in the next class. Let me just quickly give you one more maybe example, maybe like say in case of furan, also, like say if you take furan, the reactions we also did one reaction with furfural, I guess, yes, furfural, just let us say furfural, and we did this reactions with singlet oxygen in with water. So, the previous example was on pyrrole, and this is an example of furan. Furan also undergoes this addition, singlet oxygen addition, okay, and try to figure out the structure of the product. Okay. And so, we will have a little more, quite a few more examples in the next class on oxidation reactions.